Hi, my name is Daniel Antonioli. I am from EPFL, and this presentation is about our paper titled Bias, Bluetooth Impersonation Attacks. This is joint work with Nils Stippenauer from CISPA and Casper Rasmussen from the University of Oxford. Our work deals with Bluetooth security. Bluetooth is a pervasive wireless technology maintained in an open standard. The Bluetooth standard specifies two stacks, Bluetooth Classic for high throughput wireless services and Bluetooth Low Energy for low power wireless services. And we are going to focus on the first one, Bluetooth Classic. The Bluetooth standard also provides custom security mechanism and is paramount that such mechanisms are secure against attacks. One vulnerability in the Bluetooth standard enables to exploit billions of devices, including phones, tablets, laptops, and cars. In our paper, we present novel standard-compliant vulnerabilities affecting Bluetooth authentication and attacks capable of exploiting such vulnerabilities to impersonate any Bluetooth device without having to authenticate. We call our Bluetooth impersonation attacks bias attacks, and in the next slides, we will see their design, implementation, and evaluation. Before jumping into the attacks details, let's introduce our threat model. We consider two victim devices, Alice and Bob. Bob is the Bluetooth master, and Alice is the Bluetooth slave. The Bluetooth master is the connection initiator, and once the connection is established, the roles can be switched dynamically. Alice and Bob complete Bluetooth pairing and establish a long-term key. Once paired, Alice and Bob start secure session establishment, authenticates the shared pairing key, derive a session key from the pairing key, and use the session key to encrypt their session. The attacker, Charlie, should not be able to impersonate Alice to Bob as he does not know KL, and for the same reason, should not be able to impersonate Bob to Alice. The Bluetooth standard provides two authentication procedures, Legacy Secure Connection Authentication, LSC in short, and Secure Connections Authentication, SC in short. Our paper demonstrates that both procedures are vulnerable and that an attacker can exploit them to impersonate Alice and Bob during session establishment without knowing their pairing key. In the next slides, we will describe the master and slave impersonation attacks on LSC authentication first, and then on SC authentication. Let's start with LSC authentication. This procedure provides unilateral authentication using a challenge response protocol and works as follows. With the first two messages, Alice and Bob exchange their Bluetooth addresses, indicated with A and B in the figure, and they negotiate LSC support. Then Bob, the master, sends a challenge to Alice, the slave. Alice computes a response based on the challenge, her Bluetooth address, and the shared pairing key, and sends the response to Bob. Bob computes the response locally and checks it against the response received from Alice. If the responses are not equal, Bob aborts secure session establishment. Otherwise, authenticates that Alice owned the correct pairing key. In our paper, we uncovered that LSC authentication has two main issues. Firstly, it is not used mutually during session establishment, and in particular, only the master authenticates the slave and not vice versa. Secondly, a device can switch authentication role before the procedure starts by triggering a Bluetooth role switch. We take advantage of those two vulnerabilities to design master and slave impersonation attacks on LSC authentication. The master impersonation attack works as follows. Charlie presents to Alice as Bob by sending Bob's Bluetooth address, the red B in figure, and also sends LSC support. Alice sends her Bluetooth address and LSC support, believing that she's talking with Bob. Then Charlie completes unilateral authentication with Alice, ignores the response received from Alice, and continues session establishment without having to authenticate to Alice. The slave impersonation attack works as follows. Charlie presents to Bob as Alice, red A in figure, and also asks Bob to switch Bluetooth role before being asked to authenticate. Bob accepts the role switch request as it is standard compliant. Charlie becomes the new master and as a side effect also the new verifier. Then Charlie completes unilateral authentication with Bob, ignores Bob's response, and continues session establishment without having to authenticate to Bob. We've just seen how to break LSC authentication. Now let's look at secure connections. Secure connections authentication provides mutual authentication with a challenge response protocol. And for this reason is better than LSC that only provides unilateral authentication. As we can see from the figure, with the first two messages, Alice and Bob exchange their Bluetooth addresses and they negotiate secure connection support. Then they exchange two challenges, CD and CA, and they compute two responses, RA and RB, based on the challenges, on their Bluetooth addresses, and on the shared pairing key. Then Alice sends RA to Bob, Bob sends RB to Alice, and both check that the received response match the one that they computed locally. If the responses are not equal, secure session establishment is aborted. Otherwise, Alice and Bob mutually authenticate that they own the same pairing key. Even if SC authentication is mutual, it is still vulnerable to impersonation attack for two reasons that we are covering in our paper. Firstly, SC and LC can be negotiated, and such negotiation is not integrity protected. Secondly, SC support is not enforced for pairing and session establishment. This means that even if Alice and Bob support SC and already paired using SC, they are not required to use SC for session establishment. We take advantage of both vulnerabilities to design master and slave impersonation attacks on SC authentication. The master impersonation attack on SC works as follows. Charlie presents to Alice as Bob by sending Bob Bluetooth address and lies about his capabilities by proposing LSC instead of SC. Even if Alice supports SC, the secure session is downgraded from SC to LSC, and this means that the authentication procedure is downgraded from mutual to unilateral. Then Charlie performs the master impersonation attack on LC that we described before and continues session establishment without having to authenticate. The slave impersonation attack exploits the same downgrade trick. Charlie presents to Bob as Alice, proposes LSC rather than SC, downgrades SC to LSC, and then performs the slave impersonation attack on LC, taking advantage of the role switch trick. The 4 bias attacks presented so far are enough to break Bluetooth authentication. But for fun, let's assume that Alice and Bob use a fictional very secure connections mode, and that this mode does not allow to downgrade the secure connections to legacy secure connections, and uses the secure connection mutual authentication procedure. Is this mode safe against impersonation attacks? The answer is no, because very secure connections is still vulnerable to master and slave reflection attacks, where the attacker can switch role before sending his response and can reflect the received response back to the victim. Have a look at the paper for more details about those reflection attacks. We implemented the bias attacks using off-the-shelf hardware and open source software. Our attack device consists of a Linux laptop connected with a Cypress Bluetooth development board. Our implementation enables to transform our attack device into any Bluetooth device by changing characteristics such as Bluetooth address, Bluetooth name, and Bluetooth capabilities. And furthermore, the implementation enabled to conduct all the bias attacks presented so far on actual devices. Our implementation requires significant engineering effort, as it involves patches to the Linux operating system kernel and to the development board Bluetooth firmware. We open sourced our implementation, and the code is on GitHub. We used our implementation to successfully attack 31 devices using 28 unique Bluetooth chips. In this table, we present part of our evaluation results. In the first column, we show the Bluetooth chip. In the second column, the device name. And in the last 4 columns, we show a solid circle if a device is vulnerable to our bias attacks. The third and fourth columns are for the LSC master and slave impersonations, while the last 2 columns are for the SC master and slave impersonations. A dash in the last 2 columns indicates that the device does not support secure connections and can be only vulnerable to the legacy secure connections attack. We group our set of evaluated devices by Bluetooth version, and in this slide we can see devices implementing Bluetooth versions 5.0 and 4.2. In this slide, we can see the devices that we tested supporting Bluetooth versions lower or equal to 4.1. In general, all the devices that we tested were vulnerable to the bias attacks, with one exception, a ThinkPad mouse that for some reason is not vulnerable to the slave impersonation attack. Our evaluation demonstrates that the bias attacks are practical and standard compliant, as they are effective regardless of the Bluetooth version number, the Bluetooth chip producer, and the operating system of the target device. The bias attacks are particularly dangerous when they are combined with the knob attack. The knob attack is a standard compliant attack on Bluetooth key negotiation that we demonstrated last year at Usenix Security. The combination of those attacks enables to break not only Bluetooth authentication, but the whole session establishment protocol. In the legitimate case, Alice and Bob can establish a secure session by completing authentication and session key negotiation. Let's see what happens when we attack both protocols while Charlie impersonates Bob. With the bias attack, Charlie can bypass authentication without knowing the pairing key. Then, with the Nova attack, Charlie can downgrade the entropy of the session key to a very low value. Finally, Charlie can start a secure session with Alice as Bob and brute force the low entropy session key, even if it was derived from a strong pairing key that Charlie does not know. The same happens when Charlie impersonates Alice to Bob and combines the bias and the Nova attacks. In our paper, we propose a set of countermeasures for the bias attacks. Firstly, legacy secure connections authentication should always be used mutually during session establishment. By mutually, we mean 2 times. The first time with the master as the verifier, and the second time with the slave as the verifier. Secondly, session establishment should be integrity protected using the pairing key. And finally, secure connection support should be enforced across pairing and session establishment. In parallel with the bias paper submission, we disclose our findings to the Bluetooth Special Interest Group, and the Bluetooth standard has been updated accordingly. However, this does not mean that all devices are not vulnerable to the bias attacks, as patching actual devices is harder than updating the standard. We expect that most of the devices are not going to receive any patch, or the cost of patching them will be too high. For example, you don't want to recall millions of cards that cannot be patched remotely, and we experience similar issues with the Nova attack. This last slide concludes my talk. For more information about the bias attacks, have a look at our paper, our website, and our implementation on GitHub.